He kept looking for renin, but he could not find it. So the correct answer was something like this, and I have to say, really, when he told me about it, I did not know it. But it was something like this. Angiotensinogenase, okay? Angiotensinogenase is the same thing as renin. Angiotensinogenase, okay? Angiotensinogenase is same as renin. Make a note about this. If someone gets it, you know it, guys. I told it for you. Okay. So again, let me write you here angiotensinogenase, angiotensinogenase. Yeah, anything that ends with an ase, it is what? It's an enzyme. So actually, if you Google renin, oh, sorry guys, it's in Russian. But basically, it's written that it's yeah, well, I cannot just say basically, I have to show you. So yeah, okay, see? Angiotensinogenase. You must know this one. Okay, let's go back to this. Yeah, I agree. They are bitches on this one. So angiotensinogen is converted to angiotensin 1 by renin. It's an enzyme, and you know its name. And it's secreted from the juxtaglomerular cells, which are mesenchymal cells of the kidney. So what led to its secretion in the first place? Multiple things. The RAS activators lead to the secretion of the renin from the juxtaglomerular cells. The first one is renal baroreceptor. The word baro in Latin means pressure, okay? So baroreceptors mean, well, receptors of the pressure. So if you have less blood pressure to any reasons, there will be more secretion of renin. Guys, in case of heart failure, will you have activation of the baroreceptors or not? In case of heart failure. Yes, heart failure, less stroke volume, less kidney perfusion, more renal baroreceptor activation, more renin, more RAS activation, you get what? Hypertension, exacerbate the heart failure, the patient dies. Bad idea. Let's inhibit the angiotensin 1. What about the less stretching? I did not get it. I really did not get it. But if you mean, oh, okay, look, when the baroreceptors inside of your kidney gets high blood pressure, they sleep. But when there is no pressure on them, they become active, okay? So it's vice versa type of thing. When they are not having a pressure, there is no pressure on them, they become crazy and they start stimulating the juxtaglomerular cells. Other things that can lead to activation of the RAS system include the Macular Densa. Oh no, the other baroreceptor in the carotid and the aortic arch, that's totally different. This is the renal baroreceptor. The renal baroreceptor is located in the afferent arteriole. Don't forget that. Inside of your afferent arteriole, you have a renal baroreceptors. Okay, what about NaCl delivery? So the NaCl is delivered inside of your tubule. So it's filtered from here, keeps going, some will get reabsorbed, but anyway, it keeps going, and it reaches this area. So what happens at this area? What is this? This is the distal convoluted tubule. In this area, you have like a small, beautiful structure called the Macular Densa, and I'm making the Macular Densa red. And this, its function is to sense sodium, okay? Exactly, sodium sensor. And how does it work exactly? I don't want to get in details, but actually screw it, I'm going to get in details. So if we speak about the sodium, when the sodium reaches the Macula Densa, something happens. So this happens. I'm going to show it to you really quick because it's actually important. If you remember when we spoke about in the heart, I told you about some regulatory function of the kidney, how the kidney controls its perfusion, how the kidney decide if she wants its renal artery to be dilated or constricted. It's by a mechanism called the myogenic and the tubuloglomerular feedback mechanism. And I told you that I'm going to explain this mechanism for you 3 times in this book. That was the first time. Now it's the second time. So when let's speak, someone has more blood flow to his kidney, so the kidney is getting a lot of blood, so the kidney be like, come on man, I don't need that much blood, stop giving me blood. So the kidney want to vasoconstrict the vessel coming into it. Okay, so how it does so? Your afferent arteriole have a lot of blood, so your glomerular filtration is super high. So your sodium delivery to the macula densa will be super high. When the macula densa is stimulated, it will start releasing ATP, yes? And that ATP will have an enzyme working on it. It's called 5-nucleotidase. Well, why is this important? How did I get an adenosine from ATP? What is ATP? ATP is yes, of course I can. So what is ATP? ATP is an adenosine triphosphate. If I remove one, just a second, if I remove one phosphate from ATP, it becomes ADP, okay? And if I remove one, so ATP becomes ADP, adenosine diphosphate. If I remove one phosphate from that, it becomes AMD, adenosine monophosphate. If I remove one phosphate from that, it becomes adenosine. If I remove one phosphate from adenosine, it becomes anosine. If I remove one phosphate, no, you are not removing phosphate, but it becomes anosine, and anosine becomes hypoxanthine, okay, and the hypoxanthine becomes xanthine, and the xanthine becomes uric acid. That's a lot. You don't need all of this. In this graph, you only need this area, okay? The other ones you will need when we speak about gout. I will come back to this. So, okay, so more adenosine. So when you have more adenosine, adenosine is a vasodilator or constrictor, guys? It's a vasodilator, okay? You are like, what the hell? It's so Macular Densa is making us adenosine, which is a vasodilator, and I don't want that. I wanted to vasoconstrict this vessel. Why it's giving us adenosine? Well, adenosine is secreted but not into the circulation. This is important. It's secreted but not into the circulation. What does that mean? That means it's secreted locally within that region, which means it controls some secondary mediators like Angiotensin 2. Is this a vasoconstrictor or a dilator, guys? Constrictor. Excellent. And nitric oxide. Is nitric oxide vasoconstrictor or dilators? Dilators. Bradykinin. Is it constrictor or dilator? Bradykinin. Dilator as well. Okay, what about thromboxane? Thromboxane A2. Is it vasoconstrictor or? Yes, it's a constrictor. So as you can see, the increase in the adenosine can control these guys locally. So he can decide either if he want to release more thromboxane or release more nitric oxide. The exact mechanism is not required from you in the USMLE. But what I want you to know, that the main idea that the macula densa controls the increased amount of vasoconstriction or dilatation of the afferent arteriole is with these substances. And when they tell you angiotensin 2 or a thromboxane, you must know that they are vasoconstrictor. When they tell you nitric oxide or a bradykinin, you must know that they are vasodilators. Okay, so let's say there will be more intracellular calcium where? In the mesenchymal cells, okay, which control this process. Then they will modulate this guy. Adenosine is a dilator, but it works locally. It does not work on the afferent arteriole. It works on the mesangial cells, okay? It does not function on the afferent arteriole as the afferent arteriole. It just works on the mesangial cells. That's it. So, Okay, then the smooth muscle cells in this area are controlled by either by one of these guys. If they are controlled by this one, you got constriction. This one, you got dilatation. This one, dilatation. This one, constriction. Okay, and that's how you control basically. This is your tubuloglomerular feedback mechanism, and this is something how the macula densa work. Yeah, and you must know the location of the macula densa. Your macula densa is located in your DCD, the distal convoluted tubule. You must also know that your macula densa is basically a sensor, as somebody wrote. It's a sensor for sodium. Yeah, and yeah, that's pretty much it for that one. Okay, so next thing that can lead to stimulation is increased sympathetic tone by activation of which receptor? Beta 1 receptor. You are like, wait a second, where else is beta 1 receptor located, guys? Can someone tell me? Yes, it's located in the heart. Exactly, it's in the heart. Yep. Okay, is beta 1 receptor a G, Q, GI, GS, or what is it exactly? It's a GS. If I activate the GS, what happens? What happens after activation of the GS? Yep, so more GS activation, that will lead to more conversion of ATP into cyclic AMP due to activation of adenylate cyclase. So that cyclic AMP will increase something called the protein kinase A. Protein kinase A, its function is to phosphorylate stuff. So when it phosphorylates stuff, it can lead to either activation or deactivation. Yes? It doesn't matter. Well, you're like, okay, so I get it. This renal baroreceptor, when they get activated, what they will do? They go to the juxtaglomerular cells and tell them, please start secreting renin. Okay, what about macula densa? What happens to them when they get activated? When there is reduced NaCl delivery to the... Oh, by the way, you must know that the macula densa gets activated when you have less sodium reaching it. Okay, not more sodium reaching it. So, when the macula densa is activated, what it does? It goes to the juxtaglomerular cells and tell them to secrete renin. Keep in mind, the juxtaglomerular cells are not located inside of the DCT. They are in the mesenchyme, okay? They are mesangial cells. Mesangial cells means like a star-like cells, okay? So, okay, and what about increased sympathetic tone? Increased sympathetic tone, go to the juxtaglomerular cells, tell them make me some renin, which is an enzyme. So, Angiotensinogen is converted to Angiotensin 1. This Angiotensin 1 goes to the lung, to the endothelium of the lung, of the vessels of the lung, and there they have this ACE, which is the angiotensin converting enzyme, which converts angiotensin 1 to angiotensin 2. Do not forget that the ACE make you also do what? It breaks bradykinin into secondary product. So if you block the ACE, you have less angiotensin 2, but you will have more bradykinin. Is having a more bradykinin a good thing or a bad thing? Bad, yeah. Somebody is asking also AMB and BNB breakdown, correct? Well, that's naproxeline. Naproxeline is a substance that does break, it's an enzyme basically. That naproxeline break down what? It breaks down two substances. It breaks down angiotensin 2 itself. Also, it breaks down what? AMB and BMB. The breaking down of angiotensin 2 is good or bad? It's amazing, it's good. What about the breakdown of AMB and BMB? It's really bad. So they were like, okay, let's give an naproxeline inhibitor, a drug that's a naproxeline inhibitor. So naproxeline inhibitor, like a drug called scubitril. That drug inhibits naproxen. Exactly. The guy, some person wrote it down there. This is the exact thing. Scipitrate. So when you give it like a blocker of naproxen, you have more A and B and B and B. This is amazing. Yeah, we want this. We want this. But sadly, you have more angiotensin too. You are like, oh, screw this. Well, it's not working. So you do combination therapy. You give the naproxen inhibitor in addition to aspartame, which is an angiotensin 2 receptor blocker. So you protect the patient from the angiotensin 2, and you also protect you increase the amount of A and B and B and B in the patient. So this will be really, really beneficial in someone with which disease, guys? Which disease? Yep, heart failure, exactly. Heart failure. Yep, you hit two birds on one stone. Help you in hypertension, help you with heart failure, help you with everything. Okay, but actually you needed two stones for one bird. Okay, which is like the first stone is the scubitril, the second stone is the valsartan. Anyway, so okay, let's take a look. Yeah. Oh yeah. Okay, let's keep going. So we have angiotensin 2 now. Angiotensin 2 does a lot of things. It works on the hypothalamus, and that makes you really thirsty. So if they ask you, this is a really common question actually. They mentioned somebody collapsing, okay? So they were just like speaking with somebody and suddenly they collapse. Like they get in some form of shock sometimes, or a syncopial attack, it doesn't matter, or even an epilepsy. But if they ask you why do you get thirsty after such an episode, and most commonly they mention like a patient who is in a just finished shock type of thing, you know, he got like a hypovolemic shock. Yeah, so when you get a hypovolemic shock, you become really thirsty, and the reason is that angiotensin stimulates your hypothalamus. You are like, well, how the hell does hypovolemic shock lead you to be thirsty? Well, look, if you have hypovolemic shock, what is going to happen to your blood pressure? Up or down? Down. Good. What is going to happen to your renin? Up big time. Yes. Okay, renin is high. What is going to happen to the angiotensin 2? Up big time. Okay, so that angiotensin 2 go to your hypothalamus and make you thirsty. See? Okay, angiotensin 2 also can work directly on the vessels, leading to vasoconstriction, which lead to hypertension. Well, vasopressors are good, they save our lives, but when it's excessive and with no need, it can kill you actually, because it increases your afterload, yeah? So you don't want that, because your heart has to function, has to work extra to compensate for this. Also, they can constrict your efferent arteriole. Guys, if this is afferent, let me clear a little bit of this area because it's just becoming too much. Okay, so let me just make it bigger. My mom told me to clean my room. Why should I clean it? I can just write somewhere else. Okay, let's write it. So if we speak about the afferent arteriole, glomerulus, efferent arteriole, take a look. If you block, this is A, afferent, glomerulus, efferent. So if you block the efferent arteriole, this one is blocked. What happens to the GFR? Or let's say constricted at least. It's constricted. Yes, you will have more GFR because the hydrostatic pressure inside of your glomerulus has went up. The pressure here has built up, more pressure, more GFR. That is correct. So if the GFR is high, what happens to the filtration fraction? It will be high. The filtration fraction formula goes something like this. It's GFR divided by the renal plasma flow. Renal plasma flow. So if you increase the GFR, you're increasing the renal plasma flow. Let me test you on this actually. If I vasodilate the efferent arteriole, this is vasodilated. What is going to happen to your GFR? It's going to be decreased. Oh my God, you are sharp in renal. So what is going to happen to the renal plasma flow in this case? Dilatation of the efferent arteriole. It's going to decrease, yes. Because remember, the renal plasma flow is the amount of the blood that is going through the afferent arteriole to your pretubular capillary. So since this guy is basically, oh, wait a second, guys, you just made a mistake. I did a mistake, actually. When you vasodilate this one big time, what will happen to the renal plasma flow, I asked? There will be more blood going through it. So that actually will be high. If this will be high, what happens to the filtration fraction? It goes low. Why? Because it's an inverse relationship. Okay, that was good. So when the angiotensin 2 constrict the afferent arteriole, that will increase your filtration fraction, yeah? Which will keep your GFR high when the renal plasma flow is low. Initially, this is good. Initially, this is actually good compensatory mechanism, but after some times, it becomes horrible. We'll speak about it. We'll say why this can lead to basically hypertensive nephropathy. This is for later. So here you can see that your angiotensin 2 also can work in your kidney. So renal cells. We have the principal cells. The principal cells, where is it located, guys? Is it in the BCD, DCT, or is it in the collecting tubule? Collecting tubule, correct. What about the alpha intercalating cells? Is it in the same? Yes, okay, good. Okay, so here we have a sodium hydrogen activity of this channel. Let's take a look at it. First of all, I told you, do not worry too much about this page because you will see it so many times, it's annoying. So you can see here angiotensin 2 stimulating directly a sodium channel here, reabsorbing sodium and excreting hydrogen outside. Okay. So when this happens, what will happen to the patient? The following will happen. Take a look. So it works on the BCT cells, you just saw it, and that led to sodium, bicarb and water reabsorption. And when that happened, like you had sodium reabsorption inside, and what was it throwing outside? Hydrogen. Yeah, we saw hydrogen was thrown outside. Yep, here it is. More hydrogen is thrown outside. So that leads to something called contraction alkalosis. Contraction alkalosis, okay? So more water inside with more sodium inside and more hydrogen going outside, we call it contraction alkalosis. Okay, we have a substance called aldosterone secreted secondary to the increase of the angiotensin 2. Can someone tell me where exactly aldosterone is secreted from? Nobody writes adrenal, please be more specific. It is secreted from the zona. First of all, it's from the cortex. You are right, adrenal cortex. The adrenal gland, but where exactly from the adrenal gland? From the adrenal cortex. Remember, the adrenal cortex has the 3 layers. And they are GFR, yes? Glomerulosa, fasciculata, GF and R, and reticularis. GFR, glomerulosa fasciculata, and reticularis. And remember, the deeper you get, the sweeter it gets. So, exactly. So the G is for mineralocorticosteroid. An example is our friend now is aldosterone. Fasciculata is a little bit more sweeter, which means that it will be glycocorticosteroid. And finally, the inner portion will be the sex hormones. And the innermost portion, which is the medulla, basically, that will make you your catecholamines. Common question. Which sympathetic nervous system receptor is located inside of the medulla of the adrenal gland? Do not tell me that I did not ask you this. You will be seeing it in your word, in your real exam. They keep asking it. Okay? Actually, I have to say, I got it wrong multiple times. The question says, which receptor is located at your adrenal medulla of the sympathetic nervous system? Which receptor is located at your adrenal medulla? No. Actually, it's acetylcholine receptor activating sympathetic nervous system because it's considered a preganglionic area. Okay? Do not be tricked with that one. Actually, I have to say I got it wrong first time, so I don't really care about it. So, but you guys must get it right. So, it is inside of your adrenal medulla. You are having the N subclass N receptor, which is a muscarinic receptor. Well, actually a nicotinic receptor, but yeah, it works with acetylcholine. But this is the nicotinic receptor, which is for acetylcholine. Okay, just know it. You must know it. It's a factoid that they ask about. Okay, let's keep going. So the next thing I'm going to tell you about now, it's going to be, yes, so aldosterone was secreted from the zona glomerularis. You are completely correct. And that will lead to activation of the principal cells, which lead to further sodium reabsorption and potassium secretion. So more potassium going outside. And there will be more potassium conductance, which lead to, basically to more potassium movement to the outside. And sodium potassium ATPase and ENaC activity. Which drug works at the ENaC channel, guys? Do you remember? We spoke about it the other day. ENaC channel, which was here. No. Yeah, sodium channel blocker. Like amiloride and the triamterene. See, the principal cells has sodium channels, yeah? And these sodium channels can be blocked by these two guys. They do not end with one. While the aldosterone receptor blockers end with one. That's how you differentiate between the two. The aldosterone receptor blocker end with one. Okay, and aldosterone also ends with one, if that helps. Okay, so from your posterior pituitary, ADH will be released, not secreted. Where is ADH secreted, guys? Where it's made? Where is ADH made? Which organ make you ADH? It's wrong. It's not made in the pituitary. It's released from the pituitary. But where it's produced? It's produced in the hypothalamus. Then it uses like a physical system, basically neurons, that it moves inside until it reaches the posterior pituitary, the neurohypophysis. And then it's released from there, and it works in the principal cells, activating aquaporins, which are, aqua means water, and porins means like pores. So it helps to reabsorb the water. Finally, the aldosterone work at the alpha intercalated cells, which lead to hydrogen secretion, which increases the hydrogen ATPase activity, which basically, in a more simple word, it leads to a lot of hydrogen secretion outside of your body, which make you get alkalosis. Okay, so the patient who has hyperaldosteronism will get in a state of alkalosis. That's what I want you to know. Okay, guys, one more thing before the break. Can someone tell me which other hormone is released from the posterior pituitary? So yeah, oxytocin is secreted from the posterior pituitary. The oxytocin is also released from the posterior pituitary. Yep, it's the love hormone. I have 3 articles about it actually, but they are in Arabic. So yeah, that's interesting. Okay, oxytocin is actually the hormone that creates bonding between people, like between the mother and her child, you know? Like if it does not exist, the mother will never have emotion towards her child. And it's actually that's why you do like the skin to skin contact, because it increases the release of oxytocin. And really quick factoid that oxytocin is more in women than men. That's why men tend to cheat more. Yeah, I know. So, so anyway, let's take a break for now and keep going after the break. 10 minutes break, guys.